Good afternoon, everyone. This is Yusuke Okazaki in Sumitomo Corporation. I'm leading the quantum transformation project in the company. 皆様はじめまして、住友商事の
Okazaki from Sumitomo Corporation. So at Sumitomo Corporation, I lead the QX team. So using quantum computer, doing investment and other projects. So I'd like to talk about the demonstration in the financial field that we did last year. Briefly, my self-introduction. So I joined the Sumitomo Corporation. It's been about 20 years. In my early days, well, my background was chemistry and electronic materials. So semiconductors and displays, business development was what I was doing. In the latter days, I have been involved in the investment plans and startup investments is what I've been doing past 3-4 years. Today, I forgot to make an agenda slide, but this is a brief introduction of my company, and I want to talk about Mizuho Daiichi Financial Technology, which is our partner, and Classic. And so introducing them and then talk about our demonstration. So Sumitomo Corporation. So we have 9 business groups, each of the groups doing a lot of business worldwide. So quantum computing, we have done many demonstration projects using quantum computing, and we have a lot of frontline businesses where we can actually try them. And so today I'm going to talk about the financial use case. And within our group, regrettably, we don't have financial business, so we have Mizuho Financial FT to help us out as a partner. Now, we are a general trading company. And why are we working on quantum technology? So first, we have corporate venture capital doing startup investment, and we have 5 offices around the world. We started in the US, started in 1998. More recently, we have accelerator operation, more upstream, and also private equity, more downstream. And quantum computing initiatives at our company, well, that is one part of our investment portfolio at the corporate venture capital. So that's how we started. And this one slide shows our quantum computing initiatives, an overview at our company. Far left, you see our investees, 6 companies. In parallel to that, from early days, from around 2020, from the early days of quantum computing, we have been studying how it will be implemented in society, what potential it has. So we have been testing, becoming users ourselves. In more concrete terms, I mean, there's this One Sky, collaborate with One Sky that controls drones. So it's a drone simulation. And we have a lot of logistics being a trading company. So shift optimization of warehouse workers. We do that using quantum computer. And there's IMO Solutions in the Nordic countries that does car sharing. So how to have an optimal distribution of cars is what's being studied. And also now, more close to our core business, we have various investments in mines like copper and coal. And we're always thinking about how to improve operations. So quantum solutions may be introduced to improve the operation cost of these mines. So that's what we've been testing. And far right, business development. So not just our investees, but more advanced stage quantum computer players. We work with them toward a future social implementation. And so in science and in finance, what kind of applications are possible is what we have been exploring. And today I'm going to talk about Classic, which is our portfolio company, and case study that we worked together with them. So this is a classic overview slide. And Tanaka-san, head of operations Japan, explained, so I won't go into detail. But the quantum algorithm, so it's a straight through development environment for quantum circuit. So it's a quantum software vendor that does that. And this time, so this is the setup for our demonstration this time. So Sumitomo Corporation, we don't have much of a financial business. So we tied up with Mizuho Daiichi Financial Technology. So it's Mizuho invests 60%. It's their subsidiary, so it has data science and financial engineering, and it develops and provides those solutions. So financial engineering data is provided by them to us, and we collaborate with Classic. They have the software development platform. So using that, we explored what kind of applications we can work on. So that's the setup. So when we started, I think you can imagine that within trading company, there aren't so many people, or are there, who can really build up these quantum programs. Now, Classic's product works well. It allows people who can't develop algorithms using R and Python. If you have some knowledge of that high-level language, then you can work on quantum. So that's the concept of their product. And so if that's the case, we thought that we could do it as well.
That's the reason we started last year. And one more thing, when we started, the Mr. Tanaka of Classic Japan came to us and he said that this might be too difficult for you to tackle with. So his suggestion was to start with the tutorial level, and then he suggested also that we have to go to the next level after a while, to go to the level that has been handled by Mizuho. But we decided that we should go straight into the difficult part, and we were very enthusiastic and motivated, and we were able to complete all these. So as I said, we had collaborated with Mizuho Daiichi Financial Technology, and so this is what they try to realize with the quantum technologies. There could be two things: utilizing Monte Carlo simulation and also the quantum machine learning. For the Monte Carlo, this is for the derivative pricing and acceleration of the credit risk quantification and sophistication of big data analysis, and also acceleration of the training and the inference of generative AI. These are the four things that they have been working on. And this time we went on to the demonstration, and this is mainly about the two cases for the Monte Carlo simulation. As some of you may know, what kind of Monte Carlo solution is provided for financial applications? First is the credit portfolio risk management. So when you say credit portfolio, please safely understand that this is the collection of large number of the debtors. So we have large number of debtors, and then to a certain extent, with a certain level, they will not be able to repay their debt 1 year after that, or maybe several years after the event. And then there are many the customers, and then they do know that there could be a certain level of default. So what they calculate is every day is the maximum level of losses. So this is called VAR 99. That's a term they use. And what is this? They lend money to these people, and they look into the portfolio, and after 1 year, what would be the maximum level of loss? So with the 99% probability, what would be the maximum figure? That's the kind of calculation they have every day. And for this, the debtors, they have to calculate the number of debtors, and also they have to look into the scenarios with which many people would work on. For example, their pattern of behaviors, So sometimes that will be several hundred, several million, or several tens of millions. And then for these simulations, if you try to run a Monte Carlo simulation in a conventional manner, it takes time. That's the reason why they try to utilize quantum computing here. One more thing is derivative, the market valuation derivatives. So this is very difficult. In the case of derivatives, they have the underlying assets such as stock prices and exchange rates and interest rates. So this is a financial instrument that whose gains and losses are linked to these underlying assets. So it is important to look into the potential moves of the underlying assets for each and every one of them. They have to create a future scenario and based on the indicative data in the past, utilizing the financial engineering technologies and others. So this is a very difficult, complicated transactions. They have to look into the scenarios. Sometimes more than 100,000 of the scenarios should be taken into the simulation. So, and also they have to look at the payoff as an expected value. It takes time. And if you spend 1 or 2 hours for that, then during that time, the price would change. So it is important to do that in a more real time. And so that's the reason why it is important in the future to utilize quantum computing. So that's why they have to be working on this. Moving on. So this is what the Mizuho Daiichi FT is working on. So in the field of Monte Carlo, they try to work on the Monte Carlo, the quantum Monte Carlo integration with pseudo random numbers. What does it mean? So here we have the conventional method. So when the random number is generated for each random number, the registration should be made. So that means that the quantum bit or qubit have been assigned to each of them. And then against this, if you try to accumulate the qubit with the number of scenarios, it's too much. So it is impossible. That's the reason why they came up with the consecutive generation with this kind of the quasi or pseudo random numbers. So they use the pseudo random numbers to try to apply the quantum computing. So they have been working on this since 2019 when they issued a paper. And in the past they had demonstrated with Qiskit of IBM. And so this time they used the Monte Carlo simulation with the pseudo random numbers, and then a classic solution was utilized on behalf of them. So this starting last year, we have been working on this kind of experiment. And so the one thing that we noticed that the classic functions. One is the QMod, which is the high-level language. And so when they have the quantum circuits, and if you are the programmer or if you are able to write the programs, I'm sure you understand that. So when you have the circuits, it is impossible to have the actual the codes written on the screen, but rather you start with a kind of image, a kind of calculation in your mind, and then try to work on the program, the generation for the maneuvering of the gate. If you're not able to do this, it is impossible. But if you are able to use a QMod, which is a high-level language, even if you don't have any way, if you don't know how to work on the programming for the operation of the gates, it is possible. Intrinsically to put into the formula. So this way you are able to have the automatic generation of the quantum circuit with the high-level languages. So with the classic, it is possible to improve the Qiskit. So we try to run the experiment to see to what extent we are able to see the improvement of Qiskit. And so this is on the left-hand side, the Qiskit, the result, and on the right-hand side is classic. So the transfile, the path toward the transfile is about the same. Then after that, after transfiling, we looked into the depths of the circuit and number of qubits. And then I'd like to explain to you to what extent the classic is good. The parameters for the optimization is shown also in the Qiskit, but the classic parameters are very much in details, so it is possible to have detailed designation for the parameters. That was very good. This is the outcome, and this is the comparison results. And so this is based on the pseudo-random quantum Monte Carlo method. The Mizuho FT have been working on it for many years. And then please take a look at the green and blue. And so
Left-hand side. So you see the accuracy of pseudo-random numbers in the horizontal axis. So how many pseudo-random numbers do you generate? So the vertical axis is against that the number of pseudo-random numbers, how many quantum bits do you need? And as you can see, green is classic, blue is traditional tool, that will be Qiskit. So for pseudo-random number, the more of that, you need more quantum bits. But compared to the classic and Qiskit, well, you see that the number not so different between the two. Based on that, you go to the right, the line graph. So horizontal axis is the same. The representation accuracy of pseudo-random numbers, or how much volume. And then you look at the circuit depth that will be required against that number. That's the vertical axis. So classic, it's growing a little bit, but very slowly. But the Qiskit, the traditional tool, you see that the circuit depth rises quickly, so it gets more deeper as you have a larger number of the pseudo-random numbers. So what you can see comparing these two is that the quantum bit number, not so different for classic and the Qiskit, but the quantum circuit depth is quite different. You can reduce substantially if you use classic. So with the pseudo-random number Monte Carlo method, maximum 95% reduction has been observed. Similarly, using the traditional Monte Carlo method, the conventional method, I won't go into the detail because of time, but the same conclusion. Classic and Qiskit, in both cases, number of quantum bits is not so different, but the needed circuit depth could be reduced substantially. So insights from the demonstration is summarized here. First, you can reduce the depth of the quantum circuit. So quantum circuit. So you're not optimizing what's been created, but you write in high-level language, and then you create the optimized circuit. So by using classic, you're able to reduce the depths. What happens then is, well, in Q2B, many hardware vendors are presenting. There's a roadmap of 2030, 35. People talking about how to reduce the depths. And you can actually apply this in concrete use cases before that is realized. Also, hurdle to develop quantum algorithm is lowered. What I mean is that we have people at the Sumitomo Corporation. They don't have knowledge about building quantum gates. But if you can use Python and then you RS, then you'll be able to develop this. So it allows a broader range of people to do this. So this is the final summary. As I said, in anticipation of the FTQC era, for early social demonstration, software like Classic is required so that the hardware requirements can be reduced. And so I already explained the result of the demonstration. By using classic, the quantum bit number is not changed, but the circuit depth was reduced significantly. So this experiment that we did with Mizuho showed that result. But for other examples, we see that not just for the bits, but for the circuit, you can reduce them. So you don't have to wait for the hardware to grow. And you can start to use quantum computers in real cases. So that's what's expected. So I hope that we can work with you on similar projects. So thank you very much for your attention.